Welcome to the second lecture of Geology 2017. If you remember, in the first lecture we had a bit of a discussion about the intersection that exists between engineering geology and the more pure geological sciences that study the majority of the earth science processes that are devoted to understand the evolution of our planet. Processes like plate tectonics and also other processes that leads to the formation of, for example, ruptures in the crust, like faults, were object of discussion and are things that really are linked to the core of earth science. Engineering geology instead is more of a science that looks at understanding materials or geomaterials, and so we looked at a discussion of basic mineralogy, so a variety of the most abundant minerals on earth was treated, and today the idea is to continue to place more context to the mineralogical and rock variety that we find on our planet. So we will firstly go through some of the lumps because we have discussed in the last lecture most of the content of the course but didn't really address the content of the lumps. So this is really a set of lumps that are designed to address the characterization and description of minerals and rocks. So we are going to have a series of virtual laboratories because this course is essentially provided online fully this year. And so the lab 1 will involve a series of videos that look at a number of activities with minerals. Subsequently, we are going to look at igneous rocks, so plutonic and volcanic rocks will be investigated virtually with a series of videos again. And we're going to look at a series of experiences to understand differences in textures in rocks, aiming at the visual, really macroscopic features that are distinctive and can easily help you with the classification of these types of rocks. And then we will have an oral examination for these first 3 modules. That is essentially a series of questions that I will ask. We will have a number of specimens, likely 3 specimens that I will select, and I will provide you with photographs and videos, and we will discuss together when the examination date is selected and the proper time is selected. We are going to have some conversations around some of the specimens that are presented in the first 3 labs. The second part of the labs is 2 final labs on sedimentary and metamorphic rocks. We use pretty much the same formula and we complete with a similar type of exam, so another oral examination which will be a discussion that considers sedimentary and metamorphic rocks. So it's important to relate differentiation. If you remember, we discussed about the dynamics on our planet, and I mentioned several times this idea that over time our planet evolves, and this is linked to plate tectonic. But a key question we could ask ourselves is what kind of forces are causing these changes on our planet, and what are the outcomes of the these effects. So is plate tectonic conditioning in any way how our planet evolves, and can you understand how this plate tectonic is operating on the planet? So in terms of the forces, I think it is critical to understand that gravity is the main force controlling the evolution of our planet. And this occurs with a process called differentiation. So our planet is composed by heterogeneous, or at its origin it was a planetoid, so essentially a pretty much homogeneous globe composed of a combination of silicates as well as nickel and iron. And over time, what happens is that the nickel and iron tend to sink towards the core because they are denser materials, and essentially gravity is operating by separating away silicates from these iron and nickel materials, which represent essentially the sulfides that are in the core and outer core part of our planet. So you can see here an illustration of what is a stratified body. So we go from an homogeneous body into a onion-like planet, which has progressively denser materials towards its core center. Pretty much at alpha you have a separation that is the separation of the core from what is termed the mantle, and also at the most outer part we find the crust. So those are the subdivisions that are illustrated in here. Dominantly, our external crust is represented by silicates, and it will have a composition that is basaltic for its majority. Exception made for these thicker parts here, which are representative of continental crust, which usually is a bit thicker. We have that the oceanic crust is usually on the order of 7 kilometers or less, and this gets progressively thicker because of tectonic processes in continents. And so within a continent, at the root of a continent where you have an erosion, you will end up with much thicker portions of upper crust. This is the upper crust, and then we have a lower crust, and then the mantle, which can be also subdivided in upper and lower mantle, and then you have the outer core and inner core. So pretty much halfway from the center we start to get into the outer core. So as I said before, the core is composed of iron and nickel sulfides, so there is a little bit of sulfide, good abundance of sulfide in the core, and also then we have in the middle between the crust and the core the mantle, which commonly is composed of two major rock types dominantly, which are dunites and peridotites. Okay, so these are first two rocks we mentioned, but you can think of it in terms of minerals as a more enriched in magnesium. So the olivine will be the dominant mineral that we find in these dunites and peridotites. So it's very olivinic, the mantle, and it does have still a significant amount of pyroxene and feldspar. So those are the key minerals that are in the mantle. So the increase in magnesium usually corresponds to the presence of olivine. So the mantle is still very rich in silicates. in this map here you can see essentially the thickening of the crust, and so we can see that in this scale we have a representation of the approximate depth of the moho, so the Morovici's discontinuity, which is the one that separates the crust from the mantle, so this 700K, and actually no, it's this one, sorry. So this is the Morovici's discontinuity. It's right going in the middle here and separating essentially the lower crust from the upper mantle. It's interesting to see that we have thicker portions that exceed the 70 kilometers when we are in the most important active orogenies today, which are the Andes here in South America and the Tibet Plateau in Mongolia and China. And so these are really the regions where we have still present active orogenies that are essentially growing, and these orogenies are areas of tectonic activity, intense tectonization, which leads to this type of thickening. So this thickness increases are linked to tectonics, and this is demonstrated by this particular thickening occurring in areas that we know are tectonically active. So there is a linkage between the evolution of our planet and the distribution of continents. In this context, igneous rocks are formed, so the products that the Earth develops during its evolution, some of the products will be igneous rocks. And this is because often this dynamics of differentiation of the planet involves a process called melting. So melting is essentially a liquefaction process. So we liquefy because of high gradients in temperature and pressure some of the rocks, and devolatilize some water and also produce magma. So magma is melted rock, and this results in some rocks that becomes extensively more mobile, and they can migrate in the mantle and crust, and essentially this process leads to the differentiation we were talking about before. Because one question we could ask is, how do we really produce a differentiation on a planet? Is there any dynamic process that causes that? And it happens to be that we form what are called convection cells. So there are essentially cycles in which we bring up and push down rocks with differential densities, and this will result in the production of igneous rocks. So magmas are typically a mixture of molten silicate with suspended crystals and dissolved gases. So the water I was mentioning before, and also some crystals. So the minerals we have discussed, some of them will be found in these melted rocks. So it's not that everything gets melted. There is a series of reactions that occur in a melt that leads to the formation of different minerals, which are igneous minerals, okay, or igneous related minerals. And today we are going to look at the different minerals that tend to form in a magma, and we are starting to essentially relate mineralogy with the evolution of a magma. This is a very important concept in earth science, which is very helpful to differentiate different minerals and associate minerals to different type of magma. So igneous rocks are principally composed of silicate minerals, most commonly in what is called the Bowen series. So the Bowen series is essentially a sequence of minerals, and we will address this concept more in detail later. So igneous processes involves really a number of key ingredients that are usually hosted in a magma chamber. So everything starts from a pocket of melt that forms either in the crust or in the upper mantle commonly, or even in the lower mantle for very specific magma types. We will see when we talk about kimberlites or hot spots that magma can come from really deep in the mantle. So we're talking about several hundred kilometers in towards the core of our planet, and we have a number of things that are contained in a magma. So in terms of volatiles, for example, we have chlorium, sulfur, carbon, water, and these HF, so fluorines, are actually present. And what happens often is this process in a magma. So when you form ruptures in the crust, you tend to suddenly change the pressure condition. And so quite often if a magma is enriched in volatiles and you open up the cap of a bottle like this, the gases will get released. So if you create a volcano, which is an opening that connects essentially subaerial conditions with the depth condition of a magmatic chamber, the result is a liberation of gases, which is represented in this. And this can be a highly energetic process that will lead to a number of additional products. So we can generate, for example, cinerites, so eject also solids because of the rapid cooling of magma particles, and this will result in particular types of deposits that are found on the Earth's surface. And they represent essentially volcanic rocks, which are subaerial rocks that form through volcanoes. But these can have, a lot of different effects on our planet. For example, an ejection of gases and particles can influence really important sections of the atmosphere. So we can get up to the stratosphere with some of the more strong eruptions, and this leads to interactions between the sun and so the incoming light will be reflected by these clouds or ejecta, and as a result of that you get climate changes that can be affecting the environment and the biosphere of our planet. So this is to say that this process of magmatism is a large scale process and can influence not only the differentiation of our planet, but also condition really the top part of the crust in the subaerial environments. Quite often magmas will be very high temperature, so you have usually a range that goes from 700 degrees to up to 1200 for the let's say normal magmas. We can have even higher temperatures, but these happen really back in time. So Archean times were known for some specific types of lavas that were particularly high temperature, and we will discuss some example of those when we address lavas in the forthcoming lectures. But yeah, it's important to understand what a magmatic chamber is, because a lot of the rocks that form that are termed intrusive rocks will be actually the result of solidification of melts that are within a magmatic chamber. And this process is usually happening over multiple scales, so we do not necessarily have just a single magmatic chamber. We have many magmatic chambers that can form at different depths in the crust, and this will result in different phases of crystallization. Crystallization is the formation of minerals, and in these three images you see how crystallization operates within a magmatic chamber. And usually crystallization has the which is the process of formation of minerals during cooling of a magma. We can see basically what happens in the magmatic chamber, and we will realize that depending on the density or the relationship or ratio between the density of the crystals they form and the density of the magma, we will get a different accumulation of crystals. So this is commonly termed the fractionation process, because when the minerals crystallize, they usually change the composition of the magma because they are segregating certain elements, and so this change can essentially cause a change in the chemistry of the magma, but more importantly a change in the density of the magma. So usually crystallization will take away the more dense material which will accumulate at the bottom of the magmatic chamber, but in some other instances it will crystallize things that will end up floating on the top of the magmatic chamber, and this material can migrate upward in other magmatic chambers as well. So more mafic magmas tend to be concentrating at the bottom of the magmatic chamber because of this differentiation and crystallization, whereas felsic magmas will try to migrate upward, and this is a very important differentiation process that occurs in magmatic chamber in general. Here you have another example of fractional crystallization that shows you essentially that we have at the level of the mold, which is separation between the crust and the mantle again, we do have a lot of mafic minerals crystallizing. So we have magmas that tend to reside at this level and equilibrate with the moho, and a lot of precipitation of mafic minerals occurs. Mafic minerals, if you remember from the previous lecture, are ferromagnesium minerals. We have then a phase in which we reach gas saturation, and we start to liberate gases together with more felsic melts, and this results in more complex phases in a higher level that is more silicic. So this change in color is indicating that here we get more felsic minerals. You can see more white rectangles in here and less black rectangles, more bubbles, so more gaseous phases, which changes essentially the type of activity and the type of igneous rocks that crystallize and form in these other environments. So you have to imagine that several magmatic chambers can be stacked on top of each other, and this will result in different intrusive rocks forming depending on the level on the crust in which the magmatic chamber is placed, and also the level of fractionation. So fractional crystallization is the removal and segregation of mineral from a melt after crystallization. removal of crystals changes the composition of the magma. So these are the key aspects. So any crystallization will lead to a change in the magma composition. This results in a variety of igneous rocks. We can distinguish the plutonic, the hypabyssal, and the volcanic or extrusive rocks. So if we start from the bottom, the plutonic rocks will be the one that form at depth, like this example here close to the Moho, or this other example. But as soon as these magmatic chambers are become very close to surface, so this is a volcano here, and we have some subaerial emissions. So if we solidify rocks in this environment, which is usually in the first 2 kilometers of crust, then we commonly call these rocks hypabyssals or subvolcanic, and they are distinguished usually by the fact that they have usually finer grain textures. So the minerals will become smaller in size while we move up. This is an important property that helps with the recognition of hypabyssal rocks, and often they exhibit what is called a porphyric texture. At surface, let's see some ejecta, and deposition will lead to the formation of your volcanic or extrusive rocks. Usually we have a variety of products. They can have either a mafic or felsic composition. One example of hypabyssal rock in here, to give you the feeling of these crystals crystallizing, is this famous poikilotic texture. So poikilotic textures usually, or glomeroporphyritic textures, will be represented by crowded sets of minerals like plagioclase that is growing within a mafic mineral. So in this case, olivine or pyroxene. So this is a classical example of this sort of hypabyssal crystallization, where many white minerals are growing within a mafic melt, essentially. So in this slide we have an example of an hypabyssal rock, and these hypabyssal rocks are exemplified by seals in this case. So a seal is an infiltration of magma that exploits subhorizontal anisotropies in the rock. So you can see in this example these very dark colored basaltic rocks that are infiltrating likely granitic assemblages, and you can see a change or a necking process that takes place. We can clearly see that this is the rock that is infiltrating this granitic material, because we can recognize a number of veins forming in this domain. So essentially you are folding a pre-existing rock which is granitic, very competent. You are breaking this rock, forming fissures and fractures, and these are filled by the mafic minerals that are mostly plagioclase and pyroxene for the basaltic assemblage we are considering. This has happened at relatively shallow depths, because we don't really see any change at the contact, so we assume that this was already well crystallized and relatively cool if compared to the surrounding rocks. If this process would have happened at higher depths, then you would see reaction boundaries, which often tend to occur when you have significant pressures, temperature conditions that allow for a slow equilibration of these margins. So essentially you will find chill margins in this context. Now that we have an understanding of the general processes that essentially leads to the formation of minerals, and we understand also how a magma evolves through fractional crystallization, it is important, I guess, to realize that this process is not random. And most importantly, the associations of multiple minerals that form during magma crystallization follow specific laws that are governed by thermodynamics. In this sense, at the beginning of the 20th century, Norman Bowen started to experiment with powders of rock, and he basically worked with different pressure and temperatures, and firstly melted the powder and then let it cool to essentially see what was happening. And these experiments were kind of revelatory because they led him to find interesting associations of minerals. And these were translated into this diagram, which represents a summary of the mineralogical associations as well as the progression of a basaltic magma that is crystallizing over time for progressively lower temperatures. We have two series of crystallization. One is represented by the mafic minerals, the other by the felsics, and you can see a progression from higher temperatures where we form, for example, the couple olivine and calcic plagioclase, and then we go progressively to lower temperatures where we find the most stable minerals, and we essentially precipitate pyroxene, amphibole, and biotite on the mafic side, and we essentially decrease the calcium on the felsic side and increase the alkali, so the sodium and potassium, and form the other plagioclase, so alkali calcic plagioclase, and the ALBITEs at the end of that trend. And everything end up with K-feldspar, muscovite, and quartz, so the potassic feldspar as well as other potassium minerals such as muscovite are more stable at lower temperatures. So clearly what he found was that, for example, it is very hard to find K-feldspar associated with olivine because they form in completely different pressure temperature conditions. And usually the minerals that are more stable are the ones that are formed at the end of the fractionation series, so the K-feldspar, the muscovite, and quartz, because are in equilibrium with the normal temperature condition that we find at surface. So the deeper you form a mineral, the less stable it will become if it's exposed to surface. Another person that basically on the same year, so in 1922, made a similar conclusion was Goldschmidt. Goldschmidt was an eminent geochemist at the time, and in fact he was, I think, captured by University of Christiania because they essentially offered him a professorship in mineralogy, and at the time I think yes, he was really captured by this offer, and this is kind of famous because he was only 26 years old when this happened. And yes, he was interested in studying geochemical processes, and in fact is famous for sort of discovering and offering sort of a interpretation of the periodic table of elements that Mendeleev firstly discovered, and so the organization of elements were seen by Goldschmidt as, these elements were more affine to sulfur, like chalcophile elements or lithophiles and others. But he was also famous for sort of proposing these other crystallization sequence that looks at the variations in the content of calcium, sodium, and silica, and also at the type of rocks. So the difference between Bowen sequence and this classification is that here you have also an initial indication of the different rocks that are produced during crystallization. So you will find them here in the middle, and you start with the mafic compositions, so enriched in magnesium and iron minerals, and you essentially go through a set of transitions that leads to a mineralogical change, but also a change in the name of the rock type, which will be more silicic. So we go from basalt to andesites to rhyolites, and also we have sort of aqueous residual solutions, so exsolutions of fluids at the end of the crystallization. And you can see here we are producing exactly like in the Bowen sequence the potassium feldspar, the muscovite, and quartz. So it's very similar, but also has, the other important ferromagnesium minerals. So we have also accessory minerals in this series, and so we will see that basically this type of sequence is very much similar to the one we find in the Bowen sequence, but we have also here the accessory minerals, such as the chromite, ilmenite, and magnetite, which is a more oxidase phase. We will see today some examples of these minerals to complete the discussion, and also we will look at the different minerals that we haven't talked about. So for example, the calcium-rich plagioclase, so the labradorite variety, and also the sodium varieties, so that we can identify these changes, although these are very difficult to recognize actually at macroscopic scale. In terms of crystallization, here you have an example very similar to the magmatic chambers I was presented earlier, in which we have 4 phases of cooling. We go from the 1200 degrees down to 600 degrees, and we have essentially precipitation of olivine. Then we start to precipitate the pyroxenes, amphiboles, and lastly we are precipitating more feldspars in this part, which are indicated in white. So we change progressively the composition of the melt, which gets reddish in color, which could be interpreted essentially as an indication that is more felsic. So if we go back to the Bowen, we look at the first mineral, which is the calcium plagioclase, and you have also in the series to remember that there are also accessory minerals. We'll look at them later, but yeah, we start from this side and go down and look at the different feldspars. If you remember, we talked about feldspars in the previous lecture. Usually when we are dealing with plagioclase, it's more whitish in color and often has this typical twinning, which is the polysynthetic twinning, and it will look like a set of striations on the plagioclase. Quite often these have specific orientations, and in fact you can see here these are represented using the conventional mineralogy coordinates. So for this you have essentially three axes that are corresponding to the three digits, and you can think of them as X, Y, Z, and so that means that synthetic sphere will be on a surface that is normal to the Z axis, so essentially an horizontal surface, and also they will be normal to the Y axis as well, which will be a subvertical surface that is normal to parallel to north-south basically. So these are ways in which you establish the orientation of particular features on a crystal. So often if you find these numbers, they will indicate the orientation of a particular plane. So for example, a cleavage, which we learned is essentially a fracture along the structure of the crystal, will develop along the same surface. So essentially a basal surface, which is a 001, which is normal to the axis Z, which is the vertical axis. Okay, and so these are some of the features. Often the polysynthetic twinning in a thin section, which is a thin slice of the crystal, will look really like this, with repeated bands that have different extinction. So this is a bit complicated, of just to keep in mind that you can recognize these features also in thin section. So the twinning can be seen in thin section as well as the cleavages. The fracturing is often uneven to conchoidal, and the hardness is 6, so it's quite hard, but not as hard as quartz, as we have seen in the previous lecture. And the last is vitreous and has a white streak, and the specific gravity is very similar to quartz. So it's a bit easy to confuse it with quartz, but the hardness will help you in making a distinction, because you will be able essentially to tell apart. So if you try to scratch quartz with a plagioclase, it's not going to work, and you will be able to use quartz or a knife to actually scratch the feldspar. So that's an important distinction. And also usually the feldspar will be tabular, so it will have a different habit if compared to quartz. So many times also it's not as transparent, although in some cases quartz can be very similar in color. So if we move to the next one, we would look at the alkali plagioclase, which is commonly called ALBITE. So for the ALBITE, we have pretty much similar features. So we will have again a similar twinning and cleavage, and this is why it's quite kind of difficult to tell apart these feldspars, but you can recognize them and see their morphology, which is characteristic, and in this case it's slightly harder, so 6.5, has a vitreous luster like the calcium plagioclase, has a white streak, so very similar again, so very difficult to macroscopically distinguish the sodium plagioclase from the calcium plagioclase. However, it's quite easy to tell that this is not quartz, because quartz quite commonly doesn't show any cleavage. So you will be able to recognize quartz because of the absence of this cleavage. You can see here sets of parallel fractures in the crystal, which can be interpreted as cleavages, and they will have a specific orientation, and also the symmetry is completely different. In this case, these crystals are more tabular, and they do not display the classical hexagonal shape that you find in well-formed druidal quartz. Many times also you can tell apart K feldspar because so the potassium feldspar, because of iron exsolutions that occur during cooling of the crystals, which render the crystal really pink in color. We will see some examples of that color later, and that will help you with the discrimination. So if we look at the potassium feldspar, well, you can see the difference in color, a major difference. This is really pinkish in color. That will help you significantly in the recognition of K feldspar. Many times you will find that the K feldspar occur with this characteristic color. The cleavage will be present as well as twinning. However, twinning is highly penetrative, and often it helps you with the distinction of K feldspar, because the twinning is different from what you find in the plagioclase. So it doesn't have that polysynthetic twinning. Rather, it will display twinning that is like this, so the Carlsbad twinning. And you have also down here an example of how the twinning is developed. Rather than having multiple planes, you have a single plane, and it's quite penetrative. So essentially you have the two crystals are mixed together, so they are compenetrated. And yeah, pretty much very similar hardness to the plagioclase, and I guess the specific gravity is also very similar and has the same streak. So the only difference, I think, it's with respect to the luster, which is slightly more milky and often vitreous, yes, but it doesn't really, is not really very translucent. So that's another way in which you can tell apart this feldspar if compared to plagioclase, which is more gray in color and more transparent many times. So it does seem to be more closer to quartz. If you look at the muscovite, and so we work down through the felsic part of the Bowen sequence, we see essentially still a potassium mineral. So in this case we are incorporating more water. Remember that when we form minerals closer to the surface, so closer in the upper crust basically, and almost at surface, there will be a lot of liberation of fluids that come off the magmas, and these can be entrapped in minerals such as phyllosilicates. So the muscovite can host water because of the structure it has, as well as aluminum, silica, and also the potassium here. So since this is a completely different structure, because this is not a tectosilicate, we have seen that these are strata-like minerals, and in fact in this image you can see set of lamelles that represent the different surfaces that comprise the structure really of a TOT package. So tetrahedra and octahedra packages form these layers, and between the layers you will find the large cations like potassium in the structure of the muscovites. Okay, so that's really important because it tells you that you have just a single cleavage in this mineral, which is represented by all these surfaces, and often you break apart easily the muscovite along that. And in fact, if we check the hardness, it's going to be very low, and in fact you can even scratch it with your fingernail in certain instances. So you can scratch the 001 surface quite easily. So there is a huge difference in hardness, and also the habit is more platy, and as a consequence of that, it's very easy to tell apart this type of phyllosilicates from quartz, feldspars, and other minerals. Okay, so I think that's pretty much what we can say. If you remember, we mentioned already muscovite, and we said that we have a metallic luster to, I would say, pearly luster sometimes, and that is also very distinctive of the muscovites. Quartz, we have already discussed quartz a lot, and I've used it for the comparisons in the previous mineral, so it's the most stable mineral, although quartz can form at a range of pressures and temperature, and we have different polymorphs of quartz, for example cristobalite, but in this case this variety of quartz is relatively stable in subaerial conditions, for example, cavities of geopetal structures, often you will find druidal quartz, which is an indication of open space, so relatively low pressures. So how does it form? It grows essentially with a pseudo-hexagonal shape, so you form elongated prisms with a pyramid on top that is composed of 6 faces. So if you count them, you will be able to recognize it. Also, if you look at the crystals, are very translucent, and they usually have a high hardness, so hardness of 7, which scratches easily glass, and also it's gonna scratch the feldspars. So if you have a feldspar, you can try, and you will see that this crystal is harder. Density is comparable, and often you have just poorly indistinct cleavage. This is quartz is tetragonal, so you have an additional digit on the representation of the orientation of faces. So these 4 digits will indicate just that there is an extra axis that is used to represent the faces of the crystal, or the orientation of the faces. So all these digits are actually used to express the normal. So when this is 1, it means that it's normal to 2 axes of reference. Twinning can occur in different forms. I refer you back to the slide before, and I had a variety of twinning, but the most famous is the Japanese twinning, which I mentioned. So the twinning that follows the Japan law, and other things. I think I have addressed most of it. I would say also that quartz can occur in microcrystalline form, so you will not be able to see it with a proper habit, so with a proper shape. Rather, it might fill in gaps that occur in a rock, and it will essentially appear as a vein, so with an anhedral shape, so with no shape basically. Olivines are the first minerals that form often in the mantle. We have seen this at the beginning of the lecture. They represent rocks like peridotites or dunites. We will see in future lectures what these different rock types represent, but they are mostly magnesium-rich rocks, and therefore they contain magnesium-rich minerals such as olivine. Olivine is the first mafic mineral. You can see it does have a very simple structure. The variety that is particularly rich in magnesium is the forsterite. Forsterite is the magnesium end member. The iron end member is the phyalite. We'll see that later. Here you have some images of peridotite. So the peridot variety was mentioned in the first lecture, You can add cases like this in which we have essentially a lot of crystals of olivine that are crystallizing within a rock, and in this case the rock is a peridotite, so it does have a combination of minerals. In reality, if you remember the definition of a rock, we said that is essentially composed of multiple minerals, and this is a good example of that. So we have essentially a combination of darker minerals, which are likely pyroxene, and also pistachio green minerals, which are your olivine crystals. Okay, and then we have in white likely a feldspar. In this, or a plagioclase more correctly. So in this case we have a gemstone quality of a peridot, so that's an example of how it has been used by Egyptians as a gemstone. So what's the difference between olivine and the other minerals we have reviewed so far? I guess the color is quite distinctive in this case, as well as the symmetry of the crystal. It doesn't form really hexagonal crystals. I would say that the olivine is commonly orthorhombic, so you will be able to see mostly stubby crystals, but yeah, they are prisms that are slightly elongated, and yes, the twinning is not really well defined. In fact, it states here that is indistinct, and so it usually, like quartz, display conchoidal fracturing. Other aspects are the hardness, very similar to quartz, expected for a mineral that crystallizes at depth in the mantle, and the luster is vitreous to resinous on fractures, and that's quite obvious. You can see it's really translucent, especially this variety. The gemstone quality variety is very transparent. And yes, since this mineral is ferro-magnesium mineral and it forms at depth, it has a tight structure with high density of 321, 333, which is slightly higher than feldspar and quartz. So easily to differentiate that by measuring specific gravity. Okay, the next mineral that we are going to review is the phyalite. And I'm not going to spend a lot of time, but you can see the effect of iron. So increasing the amount of iron and going to the end member, that is the phyalite, exclusively composed of iron, and so you get rid of the magnesium. You start to have a completely different set of features. So for example, the color becomes more reddish when you have a lot of iron. Further to the difference in color, we can see also characteristic striations on the crystals of phyalite. You can see another example here with the orthorhombic symmetry well developed, and also a number of strias that are likely representative of the 100 plane. These striations are commonly there. If they're not propagating through the crystal, they're likely related to the growth of the crystal. You find those also in pyrite, for example. In many instances, these are again related to the growth and crystallization process. In other instances, they will be cleavage, and you can see here another crystal of phyalite that is more transparent and let you see this continuous set of fractures that are all parallel and will be more likely cleavage because they go through the crystal. And in this particular case, there were likely cleavage that is imperfect on the 100 or the indistinct one in 010. Other features that are certainly different apart the color and the type of cleavages and the density is the way in which these crystals tend to alter. So quite often solid solutions of forsterite or phyalite can alter into serpentine or other more reddish and brownish minerals like hydroxide, and these are some examples of that alteration. So essentially you get alterations that are liberating iron versus the other examples that are rather producing chloritization. So when you have serpentine, you tend to form chlorite, serpentine, and quartz and other phyllosilicates, and those are more alteration types of olivines that are more magnesium rich. Other things we can, I think, move into the magnesium pyroxene now and discuss the transition of olivines into magnesium pyroxene. So we increase essentially the complexity of the structure and move into minerals that are more, instead of being isolated tetrahedrons like in the olivines, they become chains, and we will see that we have a transition in composition also of the pyroxene that becomes more calcic while the temperature decreases progressively during fractionation. So let's discuss the first one is the enstatite. So this is a magnesium pyroxene and member, and quite commonly you see the effect of magnesium straight away on the color of the crystals, which are light brown or even white in some instances. In fact, they can be easily confused with the plagioclase. Of course, the difference here will be the symmetry of the crystals, because these are rhombic or orthorhombic in most cases, and they can also have quite unique cleavages. So we have essentially well distinct cleavages on 110 and 010, and they have a characteristic angle as well. The luster is vitreous to pearly on cleavage, and also it's important to remember that these are quite dark but translucent varieties, and they have a characteristic streak that is gray, which is completely different from the feldspars, which usually has white streak. So that's a distinguishing feature for these minerals. The hardness is very similar, and I think often the color will be instrumental in the differentiation of enstatites from plagioclase. The other variety is the ferrosilite. Ferrosilites contain dominantly iron, so they're very close to phyalites in a way, although the structure, as I said, gets more complex, but the colors and the translucency are very similar to the samples that we saw of phyalite. So difficult to differentiate, but at the same time, the difference will be the cleavage, because the ferrosilites will have a perfect cleavage again at 90 degrees, so you will be able to see two cleavages on the crystal faces, which can be helpful in distinguishing ferrosilite from the phyalites. If we move down, we start to see an increase in calcium concentration in the pyroxene, and quite commonly that translates into augites. So we have another type of pyroxene. You can see the structure is very similar. It's a coordination of silica tetrahedrons that can be partly replaced by aluminum tetrahedrons, and quite often you have a variety of cations that enter on the sides of the tetrahedron, and it's represented by either calcium, magnesium, iron, aluminum, or titanium. So calcium here is the key player, and it's going to essentially replace these other cations progressively while the temperature decreases, and most of the features are very similar. So you get this columnar from fibrous or massive crystals, but they are usually quite elongated, and they have the same type of cleavage, so the 110 and 010, and also quite often you will recognize algites because they're much darker, so they are the classical black pyroxene, which is the most frequent variety we find in nature. The streak is also different. We have a streak that is more greenish gray, and these crystals are also translucent, but many examples are relatively opaque. So since they are so dark, you don't really see the transparency that well unless you're looking at them in thin section. The luster is vitreous to resinous, and the hardness is very similar to the plagioclase and also to the other pyroxenes that we already reviewed. So it's between 5 and 6. So remember, the distinction is really the cleavage for these crystals and the color. They are really dark. If we move to the amphibole, usually amphibole has the characteristics of incorporating water. So you can see here an example of the ribbon-like structure of the amphibole. So you see a set of tetrahedrons that are essentially representing the first layer of the structure of an amphibole, and inside we have different sites where we can accommodate in some cases where you get the largest sites, you have essentially an hydroxyl that has a coordination that varies between 10 and 12 depending on the type of amphibole you are considering. This is the highest coordination because if you look at these other sites, the M4 for example, you will have a 6-fold coordination for these smaller sites. This is also important to mention the fact that you have essentially a TOT package that is characteristics of amphiboles. So you have a package that is composed of a layer of tetrahedrons that are pointing downward, and between these tetrahedra exists a layer or a ribbon of octahedrons, and below this, so this is sandwiched between two essentially layers of tetrahedrons. So at the bottom you have another set of tetrahedrons that are pointing upward. So that's the basic package. Distinction, I think, in terms of these TOT packages with respect to other phyllosilicates that have TOT packages is the continuity. In essence, they are like bricks, and so they have a finite dimension. They're quite small if compared to the continuity you have in phyllosilicates like the micas. So that's a key distinction, and that's key for hosting cations as discussed. So these amphiboles are really important minerals for the igneous rocks dominantly, but you will find them also in metamorphic rocks in different contexts, so regional metamorphic rocks as well as the contact metamorphism. We haven't discussed really a lot about metamorphism, so keep in mind that these minerals are found dominantly in igneous rocks, but you will find them also in metamorphic rock. The amphibole that we consider in this case is sensu stricto, called hornblende, and in this particular case it's the calcium and aluminium rich variety of the sensulato group of hornblende. So hornblende is a term that can be used to describe a group really of different amphiboles. But yes, one of the end members of this group is the hornblende sensu stricto, which will be dominated by calcium and also aluminum. So in terms of its structure, again, we have hydroxyl that fills the largest sites, and essentially a set of octahedral groups that represent your ribbons that are sandwiched and contain mostly magnesium and iron, and are essentially between tetrahedrons of silica and aluminum. So that's the difference is really here that at the site 0 you can host also relatively large cations, which will be the calcium in this particular case. In other amphiboles we can have substitution of other large cations such as sodium, and so you have examples like glaucophane, for example, in metamorphic rocks. So eclogites will contain a bit of sodium instead of calcium, and that represents another type of amphibole. If we review some of the characteristics macroscopically of the larger crystals of amphibole, you can see an image here that shows prism-like or elongated or columnar crystals, and essentially a section here that is either pseudo-hexagonal, or often you will find essentially lozenge shapes, which are tilted parallelograms or rhombs. So that's one of the key differences while looking for sort of recognizing this mineral against other minerals that are very similar in color, such as pyroxene. So often you will be challenged in identifying hornblende, and the main distinction is really this shape of the basal surfaces, which are, pseudo-hexagonals, similar a bit like the biotites, but the key difference is really the hardness. So it's very similar to pyroxene, and the presence of a particular type of cleavage. On the basal of a biotite, there will be no evidence of cleavage really, and so often you will find that with the end lens or with the USB microscope, you can actually detect the angle of the cleavage, which is a small and large angle as for the lozenge, which is essentially 56 to 124 degrees. Luster is vitreous to dull, translucent to opaque is the diaphanity, streak is white, and specific gravity is similar to a crystal average, so 2.9. A very abundant mineral in igneous rocks. Often you find peculiar textures in which you do find essentially clusters of radiated crystals forming that are acicular, so needle-like is quite common. Needle-like texture is quite common and is a distinctive feature of amphibole because of the fact that the crystals are very much elongated, and also you can see these losange sections in this example that are quite characteristic. So if we move to the next next on the Bowen sequence, on the sign of the ferromagnesium minerals are biotites. So biotites are phyllosilicate. Their structure is somewhat similar to amphibole in the sense that they have TOT packages. However, these are strata-like minerals, so the tetrahedron will and octahedral sites will form essentially foils of atoms that are all connected, and the large cations quite often are sandwiched regularly between these TOT packages. So that's the main difference, because basically you are essentially putting the water, so hydroxyls, will sit essentially within the octahedral sites. We can see example here of biotite. So this clarifies a little bit what I was discussing. If you look at the structure, so this is the idealized structure of the biotite. You can see in white here oxygen coordinating with silica or aluminum, and down here you have the octahedral site, and you can see here the hydroxyl and oxygen dominating coordination with the magnesium in this particular example of biotite. Because if you look at the formula up here, we got here the magnesium. It's one of the two sort of substitutions you have in these sites, the octahedral site, with the sort of coordination with aluminum and silica. So in this case, some of the silica is coming from these tetrahedrons here, so you complete this strata-like geometry with another layer of tetrahedrons, so the TOT structure. And you can see here this is larger sites that connect multiple packages through the usage of, for example, potassium or sodium or other big cations such as calcium can actually fit in these larger sites. And so pretty much similar to what happens in the amphibole, but at a different level. So in this particular case, you have larger sites that are occupied by these large cations instead of the hydroxyl, which ends up being within the octahedral sites. So this, of course, forms layers that have connections between the tetrahedrons that form hexagonal bonds, and this translates in macroscopic features in the crystals of the biotite. So you see basically this characteristic hexagonal shape, which is inherited from the atomic structure or molecular structure of this compound. So as you see here, you have that the crystal habit is micaceous, has a platy texture. Of course, these are all layers, and so you get this platy texture because you can break bonds in this at this level where you have the large sites, and so you have weaker bonds, and this explains why you have a perfect cleavage on the 001, which is the basal. So that's really critical for the discrimination, and it's also indicating and justifying why the hardness is is slightly lower if compared to pyroxene and amphibole, so we go down to 2.5 to 3, which is in reality a good difference. In fact, you can separate the two by looking at using a copper coin, for example, which would not scratch amphibole, but it would definitely scratch the biotite. Vitreous to pearly, so difference is that the muscovites usually are more, they have a luster that is more metallic and more goldy in color. And also, yes, the biotite is still transparent, but much less if compared to the muscovite. So often this is opaque and translucency is limited, especially when you have a lot of strata. So if it's a thick piece of biotite, in that sense, it will be harder to see through it. Streak is gray, which is helpful, but not very often. So sometimes also the muscovite will have a gray or greenish streak, which is confusing. But many times muscovite, as we said earlier, it can be white, and so you can distinguish them. Specific gravity, it's 3, so it's a bit higher than what's seen before for the amphibole. The last group of minerals that it's worth mentioning as part of the Bowen sequence are the spinels. Spinels are a complex group. They are essentially oxides, and they usually represent what are termed as accessory minerals in the fractionation series that we have considered. So this means that they are quite rare and they occur essentially in small percentages if you consider the whole package of minerals. So the spinels often will be associated, for example, with olivines and calcic plagioclase, and so they will occur in igneous rocks of mafic composition, from basalts to ultramafic rocks, basically. We are going to review a couple of spinels. It's important to stress the fact that these are fractionation series as well, so the composition of the spinel will tend to change while we increase, for example, the amount of volatiles in the magma. So we change essentially conditions such as the oxidation state of the magma, so availability of fluids, and will condition the redox, so availability of oxygen, and as a consequence of that, we have chromites and magnesium-rich spinels that usually occur at the beginning of the fractionation, and then we get to more magnetite-rich compositions for more fractionated products that are more enriched in silica. So ultramafic rocks will have that tendency to host chromium-rich spinel, and a basalt, for example, a tholeite, will have a significant amount of magnetite. And in fact, we are going to review these two minerals. Of course, there are many other spinels, and the most, I think, important is to mention is the sensu stricto spinel, which is the magnesium aluminum spinel. So spinel groups can host a variety really of cations, including zinc, including, as I said before, chromium, titanium can go in the structure of the magnetite, for example, and so we can form titaniferous magnetites, which are also related to the fractionation of basalt specifically. So lots of different minerals really, but they have similar structure. And here you have a representation of the structure, which is commonly still represented by tetrahedrons in coordination 4 and octahedrons in coordination 6, but we have essentially different, and this is the structure of the magnetite as an example, so an oxide of iron, and we do have that different valence of iron will play a role in the structure, and so it will essentially bond either to tetrahedron or octahedrons. So we have essentially a number of layers composed by either this relationship between octahedrons and tetrahedrons, or they are more represented by oxygen layers. So all these layers tend to be parallel to the 111 phase. So they essentially form a set of inclined planes, and these are again alternated planes containing either oxygen or combinations of tetrahedrons and octahedrons, or also cases in which you have exclusively the octahedral layers. So it's really complex, but at the same time relatively simple to see the structure as a set of 111 planes that are alternating in composition. So the first example is the magnetite. So we mentioned that already. Magnetite was also reviewed in previous lecture, and it's essentially characterized by its strong magnetic property. So a magnet will be strongly attracted to magnetite. You have here the formula, which is essentially a mixture of bivalent and trivalent iron that is coordinating oxygens, as stated before, and also remember that structure I was mentioning. So it's mostly a cubic mineral, and it forms, because of that, octahedrons very often when in euhedral form. So if the mineral has a proper shape, it's going to form these octahedrons. You have two images here for different compositions. The more iron it has in its structure, as it can incorporate other things like titanium, for example. So lots of iron will tend to give it this metallic luster. This other example is rather more vitreous, and this is a consequence of the amount of iron in the structure. But you have beautiful octahedrons, quite hard, 5.5 to 6. Some of the spinel have gemstone quality, like the one that has magnesium and aluminium. So the spinel sensu stricto will be gemstone quality in many instances. You can think of the ruby or the balas ruby, which is pinkish, famously pinkish, and these have essentially a hardness that goes up to 7.5, so they are harder than quartz. So that's an important characteristic of the spinel family. And yes, luster metallic, these are opaque in thin section. So if you look at the microscope, using the microscope, it will be opaque, like the hematite, but the streak is black, which is the key characteristic, and helps with the distinction between hematite and the more reduced variety of magnetite. This is a heavy mineral because of the density of the cell. It does have numerous atoms, for example 28 oxygens within the cell, plus as well a huge number of atoms of iron. I think on the order of 32 oxygens and 24 cations, so 24 irons, so my mistake, and the oxygens will be 32. Other aspects, I think the magnetite is part of a series, and it will be easily form solid solutions, for example, as I said, with titanium and also with chromium. So it's important to keep this in mind, and also to keep in mind that it can be forming interlocked crystals, and it's quite a massive as well, so it doesn't really have always these octahedral crystals. Okay, the next mineral is the chromite. So I was mentioning it before. These both actually, the magnetite and chromite, will be found in ultramafic sequences. They often form layered or banded formations. For example, the magnetite is abundant in the Bushwell complex together with the chromites. So the Bushwell complex is a big ultramafic intrusion, and yes, these are they're often called orthomagmatic deposits because they are essentially forming by assimilation or accumulation of these oxides within layers of within a magmatic chamber. Okay, we mentioned the idea of a magmatic chamber in the previous lecture, I believe, or at the beginning of this lecture. So this is quite critical. Often you can concentrate magnetite and chromites within these very large and thin intrusives. Okay. Some of the characteristics here, you can see the formula. So it's still a cubic mineral. It does have these characteristic octahedrons forming, and it can be also massive, as illustrated in this figure here. So here you have these octahedrons. They're not as well formed in this specimen, but yeah, often they can have a proper habit as similarly to the magnetite. The difference, I think, is the streak. It's commonly brown, and they have a similar coloring if compared to magnetite, so they are difficult to tell apart, really. But yeah, in this case, the difference will be really that these chromites are weakly magnetic. So they can be distinguished because you could mix them with hematite, but the streak will be brown, so rather than being red, and that's the important difference. As I stated earlier, these are common in ultramafic rocks, like the Bushwell complex contains dunites, for example, or gabbros, and so in magnesium-rich rocks, you will tend to find also chromium in good amounts. So the peridotites, the serpentinites, which are essentially a product of alteration, hydrothermal. We will see what alteration means, but is essentially the change in mineralogy in relationship to hydrothermal fluids reacting with rocks. This process will form serpentinites, so these are other rock types that are extremely rich in magnesium, and they're usually the product of alteration of peridotites. And so you will find disseminated grains or layers within these ultramafic assemblages. In summary, we have sort of gone through a number of minerals today and in the previous lecture that are the most abundant minerals in the earth crust as well as in the mantle. So critical certainly are silicates for the crust, because silica is a product of fractionation. We have seen that crystallization tends to enrich the amount of silica in a magma, and you can see that because at the end of the Bowen sequence you crystallize free quartz. So a complete understanding of the mechanical properties of a rock is important for engineers, and minerals represent the key controls on the geomechanical properties. You can think of muscovites or biotites, which we discussed in this last part of the lecture, and I think that's a good indication that the structure of a mineral can make a compound really weak, so you can easily break it down, and so you have a dramatic change in hardness because of the strata-like geometry and the type of bonds that occur. So your anisotropy essentially in rocks is an important feature that often has been discounted by engineers, which tend to crush the material and measure its mechanical property in a crush form. The rock texture is also important. We discussed this very little because we're not really delving with rocks as yet, but certainly it's important for an engineer to understand the concept of stability of a rock mass and the structures that exist in a rock mass are critical because they influence the geotechnical behavior. Examples of engineering relevance are the swelling of clays. So if we think in terms of minerals, we reviewed in the first lecture the different type of clays, and we saw that we have clays that incorporate a significant amount of water. So this can be a big challenge for the aspects related to construction or building construction. So it is necessary by an engineer that developed foundations, for example, to know really well the composition of the clays. We haven't talked about the example B, which is a reaction of anhydrite and gypsum with cement. I think this is an important aspect, so understanding the mineralogy and mineralogical composition of a cement that is used to construct something like a bridge is really important because over time the chemistry can change, can evolve, and for instance the abundance of sulfur, so in the form of anhydrite and gypsum, which are sulfates, as reviewed earlier, they will tend to extensively react with the iron contained in the cement. So if you have armors, they get essentially attacked by reactions with anhydrite and gypsum that is essentially liberating H2SO4. So sulfuric or sulfuric acid is the main issue because it then interacts with the iron bars within the cement and cause instabilities, and as a consequence of that you get that you lose the mechanical strength of the cement. And this concludes this lecture, so it's important to remember that there is a key association between minerals, and this is governed in intrusive rocks or igneous rocks by the Bowen and Goldschmidt series. So it's important to relate mineralogy to essentially the phase of crystallization that you are observing in the rock. So mineralogical associations can be seen through the Bowen sequence. If you can understand the mineralogy, again, you will be able to understand what kind of problems might arise if you are developing any working on a site that has that specific mineralogy and rock types. In the next lecture, we are going to improve again our understanding of tectonics, and we will expand further these concepts. We will leave the minerals and start to talk about igneous rocks more in detail, and we will try to understand how we classify igneous rocks, which is the first real challenge for a geologist that is dealing with petrology. So let's see this continuation in the third lecture.